Hi, my name is Peter Arnold. I'm studying the Bachelor of Engineering Civil Discipline. The topic that I'm going to talk to you about today is in regard to elastic and plastic deformation. By the end of this presentation, you should be able to understand exactly what is elastic and plastic deformation, as well as some definitions that will enable you to better understand these concepts. Also, how and why they occur, as well as some examples of each definition. We all know from Newton's third law that for every action there is an equal and opposite reaction, and therefore, for a structure to remain stationary, it needs to be in equilibrium. All structures are subject to different types of loads or stresses. Therefore, the structure's materials need to resist these stresses for it to remain structurally sound. To allow this, a material needs to have certain properties for its given application. When a material is subject to a force, it will undergo some sort of deformation. This material deformation leads us to the subject at hand, elastic and plastic deformation. To understand elastic and plastic deformation, it is important to first understand stress and strain and their relationship with one another. Stress describes the ability of a material to resist external forces. Ultimately, the material will come to a point where it can no longer resist the external forces applied and will fail. Stress is equal to force divided by area. Strain describes how a material changes shape under tension or compression up until the point of ultimate stress or failure. Strain is equal to the change in length over the original length. Solids or materials are classified according to the nature of the bonding between the molecular structures. It is this bonding that enables elastic and plastic deformation to occur. As can be seen in the elastic deformation figure part 1, the structure is nicely lined up next to each other. As a small force is applied in part 2, the bonds stretch. After the force has been released, it can be seen that the structure takes its original shape. This is known as elastic deformation. In the plastic deformation diagram, however, it can be seen that after a larger load has been applied, upon release of this load, the structure of the solid has not returned to its original shape. This is due to the shearing of some of the bonds, and therefore slightly altering the structure of the material. These bonds reform in their new position, ultimately changing the shape of the material. The combination of stress and strain is represented by Young's modulus, also known as the stiffness ratio. This is defined as the force needed to deform a material. Young's modulus is quite high for materials like steel, but very low for materials such as polymers. Elastic deformation can be seen as the linear part of this graph. This region represents where the deformation of the material being affected by a force returns to its original size and shape after the force has been removed. Once the material reaches the yield strength, it is said to then become plastic. This is where the material no longer takes its original form once the load has been released. The yield strength is crucial when designing products such as fasteners and bolts. Beyond this limit, the material can no longer perform as it should for its given application. For some materials and their applications, the plastic region is essential for their intended use. For example, gold and silver need to enter their plastic phase in order for them to be worked into different shapes for jewellery. When a material reaches the point of ultimate strength, this is the point of failure. This material will no longer be viable and will need to be replaced, is unusable. Obviously, for applications such as bridges, a material reaching this point will have a catastrophic effect. Elastic and plastic deformation can be further illustrated by this diagram. Stage 1 shows a spring with no force applied. In stage 2, the spring has a small force applied. As this force is removed, as can be seen in stage 3A, the spring has returned to its original shape. Therefore, the spring was undergoing elastic deformation. However, in stage 3B, it can be seen that the spring did not return to its original shape. Therefore, it has undergone plastic deformation. The spring will no longer perform as it was intended and will need to be replaced. The elastic and plastic deformation of a material will vary greatly depending on the properties of the material. As can be seen in this figure, mild steel initially has a nice straight line. This indicates that mild steel can withstand quite a bit of stress and still remain elastic. This is why mild steel is very good in applications such as structural elements for buildings. It is very different from the line graph for cast iron. This line does not have a distinct straight line section. This indicates that cast iron does not undergo elastic deformation. This is due to the material being quite brittle in nature. I hope that from this presentation you will take away an understanding of stress and strain and how Young's modulus is derived from these two factors. You should also have gained a better understanding of the principles of an elastic and plastic deformation and how they are relevant in an engineering context. I hope you've enjoyed this presentation. Thank you for watching.